Modern convolutional networks operate with an immense internal scale. A standard architecture contains millions of individual parameters, creating a mechanical mismatch when trained on a typical, highly constrained enterprise dataset. Initializing a network of this size from scratch, using only a few thousand samples, results in a system with far more internal capacity than it has data to learn from. Because the parameter space is so vast, the network skips learning underlying visual patterns. Instead, it utilizes its massive capacity to memorize the exact training samples point by point. This specific failure state is catastrophic overfitting. The model will yield high scores on its training data while possessing zero ability to generalize to new images. Data scarcity acts as a rigid structural limit in deep learning. Bypassing this limit requires an alternative to standard hyperparameter tuning. The solution involves leveraging universal mathematical priors extracted from massive datasets, such as the 1.2 million labeled images within the ImageNet corpus. Millions of cycles of backpropagation on that scale force the earliest layers of a network to identify foundational visual geometry, such as how light forms curves, lines, and edges. Adapting a massive pre-trained model to new data is a highly conditional engineering problem rather than an automatic process. This decision matrix maps the precise conditions for task-specific adaptation. The entire workflow is dictated by two strict constraints: domain similarity and total dataset volume. Successful fine-tuning requires strategic architectural intervention throughout the training loop. We begin the decision matrix analysis by isolating the y-axis variable, domain similarity. The early layers of pre-trained networks act as universal feature extractors, mapping primary visual primitives like curves and sharp edges. However, certain domains lack overlap with these standard visual primitives. Medical radiography and Chinese handwritten characters, for example, do not share the underlying geometry of the ImageNet corpus. If the new context shares no underlying geometry with the pre-training data, the learned priors are mathematically useless. For these radically divergent contexts, the network must be initialized and trained entirely from scratch, regardless of the data cost. On the x-axis, we must consider highly constrained dataset sizes within a similar domain, specifically those containing fewer than 1,000 samples. Even with transferable features, running backpropagation on fully connected layers with microdatasets will trigger overfitting. This scenario requires a specific architectural bypass: bottleneck feature extraction. The extraction mechanism intercepts the data flow at an intermediate layer immediately prior to the fully connected layers, routing those activations outward. We then feed this raw extracted feature data into an independent linear classifier, bypassing the original network tail entirely. A support vector machine is utilized here due to its mathematical ability to draw high-margin decision boundaries when sample counts are in the hundreds. Extreme data scarcity requires using the CNN solely as a fixed feature extractor to feed a low data algorithm. The operational sweet spot for active fine-tuning consists of high domain similarity combined with a dataset of a few thousand raw samples. This assumes standard data augmentation, like translation and rotation, and horizontal flipping, are deployed to maximize sample counts. Preparing the pre-trained network for active backpropagation requires three strict structural modifications. Modification 1 is truncation, the mandatory removal of the network's original 1,000 category classification head. We then initialize and append a new softmax layer that matches the specific category count of the new task. Modification 2 is learning rate suppression. Applying standard training rates to pre-trained weights will distort the existing features too quickly. The initial learning rate must be dropped by a factor of 10 to protect the pre-trained priors. This severe suppression prevents the rapid erasure of the valuable visual geometry the network has already learned. Modification 3 is layer freezing, which protects the earliest feature extractors from any weight updates. By selectively disabling backpropagation for the first several convolutional blocks, we create a hard barrier for backward data flow. This forces the network to focus its limited weight updates strictly on learning dataset-specific features in the subsequent layers. Active fine-tuning is an exercise in operational constraint, locking the universal layers, swapping the specific tail, and slowing the mathematics to prevent catastrophic interference. Pulling back from these surgical mechanics reveals a systematic landscape for deep learning adaptation. If the domain diverges, accept the data cost and train from scratch. For micro datasets under 1,000 samples, deploy a support vector machine. For moderate datasets, apply 3 constraints: truncate the softmax, suppress learning rate, and freeze early layers. Adhering to these strict heuristics ensures the model learns the underlying patterns of the new data rather than simply memorizing the training set. Success in large-scale deep learning depends on strategically adapting existing weights to fit these rigid data boundaries. Large-scale pre-trained models function as reservoirs of mathematical priors rather than ready-made solutions. Exposing these priors to new data without architectural protection leads to their destruction through overfitting. Model optimization relies on knowing exactly how to constrain a network so it absorbs new contexts without overriding its universal knowledge. Navigating this decision matrix ensures that the network's internal weights remain optimized for the target task while retaining its foundational depth.